All right, hello everyone. So in this video, we want to finish up um, the section on derivatives, and in particular, we want to do that by looking at Taylor's theorem. Um, so hopefully you've read the section here already, and it gives a little background of sort of the history of this. We call it Taylor's theorem, but Taylor probably wasn't the first one to actually look at this, and furthermore, these ideas have been built upon by a number of other folks. But nevertheless, it's most commonly referred to as Taylor's theorem. And the idea is sort of how can I approximate a function in terms of a polynomial where the coefficients of that polynomial somehow end up depending on the derivatives of this function. Now, the book again gives sort of a nice exposition on sort of, why, for example, in this formula do we end up with like where do those coefficients come from? Why are they sort of the natural things to use? I'm not going to emphasize that because many of you have hopefully probably seen it before. This would often be the way I would sort of motivate this in a Calculus 2 class. But we really want to look at this and do some analysis and see sort of why this theorem is true, and not so much on the conceptual development of it. So here's the theorem. So if the nth derivative of f is continuous on the closed interval AB, and if the n plus first derivative of f exists in the open interval AB, then for x in the closed interval AB, there is some point C in AB such that the function f of x can be written as the sum from k equals 0 to n of the kth derivative of f evaluated at a over k factorial times x minus a to the k. So this whole term here is a sum plus, and this is really almost sort of like an error term, right? So kind of plus everything else, but this everything else term has a nice interpretation, which is the n plus first derivative of f evaluated at this point C over n plus 1 factorial times x minus a to the n plus 1. Okay, so a couple of things. So this first piece here, this sum, is what we often would refer to as just the Taylor polynomial. So I could just call this the Taylor polynomial of degree n. And for our purposes, we're going to call this T sub n of x, right? So this is just for the Taylor polynomial piece, and then again, this term sort of ends up accounting for the difference here. Okay, but again, notice that this is equality, right? This isn't an approximation. There's some c value in the interval AB, so that this holds exactly. Okay. Okay. So let's look at this. Okay, and in particular, what we want to look at here is the proof of this function. Or sorry, not the proof of this function, is the proof of this theorem. So let's see. So let me start here. So again, we're going to fix, oh, sorry, this is the proof. So the first thing I'm going to do is I'm going to fix x in AB. Okay. So again, let me sort of emphasize something here and make this clear. So if I have an x in my interval AB, then there is this point C such that this holds. Okay, so it's important to note that as you change your value x, this isn't really, like this x is fixed. So we actually shouldn't think of this left-hand side so much as a function because my x value is fixed. And for that fixed x value, there will be a C such that this holds. However, for every different x value, there could be a different c value. So it might be tempting to look at this and think that if x didn't have to be fixed and the same c worked for everything, then essentially what you would be saying is that f of x is a polynomial. But this certainly applies to lots of functions other than polynomials. So what this is saying is for a fixed value of x, I can choose this value of c such that this whole piece here holds. Okay. All right, so we fixed our x in the closed interval AB, or in the open interval AB. And now what I'm going to do is I want to look at this function. So I want to define a function phi. So my phi of x, or actually let me call it phi of t, sorry. Okay, because my x is fixed, but I want to think of a general function. So here's my variable t. I want this to be f of t minus the nth degree Taylor polynomial at t, where again, I'm thinking that's just this expression sitting here, minus k times t minus a to the n plus first. Okay, where, and now I've got to tell you, so all of this is defined so far except for k. Okay, so where k is chosen so that if I plug in x here, sorry, so that phi of x is equal to 0. Okay, so I want to choose a value of k so that when I plug in x, I get 0. And you might say, well, how do you know you can choose such a k? Well, imagine I plug x in here, right? So if I was to plug x in here, I get f of x minus t sub n of x. Those are just now some fixed values, minus k times x minus a to the n plus 1. Okay, so really what I have here then is the only thing that I'm varying now is k. If I choose k very, very large, I'm going to go to either positive or negative infinity. If I choose k very, very small, like let k go to negative infinity, then I'm going to go to the other value. So by the intermediate value theorem, somewhere in between, there's a k value that makes this 0. Okay, so I can in fact choose k so that when I plug x in here, I get 0. Okay, all right. Now I can note that this function phi is n plus 1 times differentiable. Okay, why is that? Well, I know that f, by assumption, is n plus 1 times differentiable. T sub n is a polynomial, so it's actually infinitely differentiable. And this is also a polynomial, so it's actually infinitely differentiable. Okay, so this whole function is at least n plus 1 times differentiable. Okay, so let me sort of start taking derivatives. Okay, and actually I'm going to take n plus 1 derivatives. So let's think about what happens when I take n plus 1 derivatives of this function. Well, I take n plus 1 derivatives of this, okay? Now I'm going to take n plus 1 derivatives of this Taylor polynomial of degree n. Well, you can think about this in small cases, right? So what happens if I take 4 derivatives of a third degree polynomial? Okay, so take x cubed, start taking derivatives. So the first derivative is 3x squared. The second derivative is 6x, hold on, let's get this right, is 6x. The third derivative is 6, and the fourth derivative is 0. Okay, and in fact, right, this is true in general. If I take n plus 1 derivatives of a polynomial of degree n, I'm going to get 0. So the n plus first derivative of this Taylor polynomial of degree n is just 0. Okay, minus, okay, now let's see this piece. So every time I take a derivative, this factor comes down and I have n plus 1 of them. So I'm going to get k times n plus 1 times n minus 1 times n minus 2. So I'm going to end up with n plus 1 factorial here. Okay, so there's my n plus first derivative of this function phi that I've defined. All right. Well, now I'm going to actually use Rolle's theorem. Okay, so recall that, well, if I plugged in a to my function phi, what would I get here? I'd get f of a. Okay. Here I would get 0. what would I get if I plugged A into this thing? Well, you might think, oh, I'm going to get 0, but you have to be careful because when this is 0 here, that's 1, and this is just f of A. So I actually end up with f of A minus f of A, and so phi of A is 0. So is phi of x, right? I chose that k value so that phi of x was 0. Okay, well, if phi of A is 0 and phi of x is 0, then I feel sort of the hypotheses of Rolle's theorem being met. Okay, and so by Rolle's theorem, so what do I get by Rolle's theorem? There exists, and let's see, what do I want to call this point? Probably not, let's call it x1. So there exists x1 in the interval ax, so that phi prime of x1 is equal to 0. Okay, maybe not immediately clear how that's going to help yet, but let's keep going. Well, what if we tried to, let's see, I'm going to erase this piece now. Okay, so what if I sort of keep going? What if I tried to apply Rolle's theorem now to phi prime? Okay, so if I try to look at that, let's see. Also, so what can I say about phi prime of A? Well, if I look at phi prime of A, what's that going to be? That's going to be f prime of A minus t sub n prime of A, but t sub n prime of A is just going to be f prime of A. And this will be minus k times n plus 1 times A minus A to the n. So A minus A is 0, 0 to the n, so that's 0. So I just end up with f prime of A minus f prime of A, which is again 0. Okay. Well, guess what? Phi prime of x is also 0. Okay. So you can check this. So, but I want to kind of get the sense of what we're doing here. So phi prime of A is 0. Phi prime of x1. Oh, sorry. It's not phi prime of x. It's phi prime of x1 is 0. Sorry, and phi prime of x1 is 0 because of our choice of x1. Okay. So what does this mean? So by Rolle's theorem, there exists an x2 in the interval a x1, so that phi double prime of x2 is equal to 0. Okay, now you're maybe starting to notice I can sort of generalize this. So in general, I'll be able to choose xn plus 1 in the interval a to xn so that the n plus first derivative of phi at x sub n plus 1 is equal to 0. Right? I sort of keep on with this process, right? So now that I've got phi double prime of x2 is equal to 0, if I look at phi double prime at A, that'll also be 0. So now I've got phi double prime of A and phi double prime of x2 both equal to 0. So I can apply Rolle's theorem. That gives me some point that I'll call x3, which is in the interval A to x2, such that phi triple prime of x3 is equal to 0. Okay, and I just keep repeating this process until I get to the n plus first derivative. And you might wonder, well, why stop there? Well, beyond the n plus first derivative, I don't know anything about the differentiability of f anymore. So I'm kind of stuck there because I can't go any further, but I'll sort of stop here, okay? But now I'm going to claim that there's sort of a problem here, or not a problem, but I can sort of draw some information from this. So let's look at, what is this? Well, we said this was just equal to this. So if I plug in here, I have that phi n plus 1 of x sub n plus 1. Well, if I plug that in here, this should be f, sorry, the n plus first derivative of f evaluated at x sub n plus 1 minus k times n plus 1 factorial. But from this previous step, I also know that that's 0. So if I solve here, I can actually solve for the value of k. This implies that k is equal to the n plus first derivative of f evaluated at this point x sub n plus 1 over n plus 1 factorial, right? And if we just call this x sub n plus 1 c, right, it's just the point we ended up with, then we have that k has exactly this value, okay? And so going back to our original sort of statement, we now know that I just take this x sub n plus 1 to be equal to c. I'm sorry, I've erased it now, but that's exactly the coefficient that I want, okay? So this sort of proves Taylor's theorem. This is super useful, and we'll see some, I'll give you some examples in the exercise set to see where sort of Taylor's theorem can be really useful. But the book also gives a really nice example of how this sometimes is also not very useful. So, and the book calls these sort of functions that are exceptionally flat at a point. So I'll let you work through the calculations, and the book supports some of this, but just for our discussion, if we look at f of x is equal to e to the minus 1 over x squared when x is not equal to 0, and 0 when x is equal to 0, it actually turns out that this function is infinitely differentiable, and all the derivatives are continuous. So it's actually a really nice function. But if you evaluate the derivative at 0 for any value, so take the first, second, third, fifth, 900th derivative at 0, it's going to be 0, which means that when you write the Taylor polynomial for this function of whatever arbitrarily large degree you would choose, you're going to get 0. So, I mean, I think the intuitive sort of thing to keep in mind here, right, is that these are really good at approximating functions locally. But in some cases, locally is really just like at the point, right? I mean, at the point, this does an exceptionally good job of approximating this function. And in fact, even if you get a little bit away from the point, it's still not too bad, because if you look at the graph of this function, I mean, the graph of this function essentially looks something like this. So, I mean, it's not, I mean, in some neighborhood, 0 is a pretty good approximation of this function. But it's also, it sort of loses any interesting properties of the function, right? You wouldn't really look at this function and go, oh yeah, that's definitely a lot like 0. So these are useful, but sometimes also not. When you look at things like radius of convergence, right? The problem really is that even if you look at the full Taylor series, it only converges at the point x is equal to 0. It doesn't converge for any other values. So again, you can, it'd be a nice, little exercise, refresh yourself on some Calc 1 and 2 to actually calculate the Taylor series for this, but you'll actually find the Taylor series is just the 0 function. All right, so we're going to stop this video here. There will be another video for this week, and it will be sort of our going back to integration and looking at some of that more in depth. But we'll stop this video here, and that concludes our discussion of 2.3.